Hello, everyone, and welcome back. So today what we are going to do is we are going to look into another way of solving these beam problems, okay? And so this is the second lecture on beams, and we are going to do a lot of examples to understand a little bit more about the physics of what's happening behind when we are trying to solve the problem with the stiffness method. I hope that this will also give you more physical intuition, and then you will see that okay, they're very straightforward problems. And so let's get started. So what we have learned in the last class is the stiffness matrix for the beam element. So we have actually a 4x4 stiffness matrix like this here, and actually it relates the nodal displacements. Those are vi, theta I, vj, theta j. There are four nodal displacements, two at node I and two at node j, to the nodal forces. Nodal forces are pyi, mi, pyj, mj. So p and pyi I and pyj is actually the vertical forces, or these are the shear forces at node I and j, and mi and mj are the moments. Okay, so these are the moments at node I and j, and they are related through this stiffness matrix. And in the last class, actually, we solved the differential equation of the beam to find this stiffness matrix. But we didn't get any physical intuition, like what is the meaning of these entries. So um, let's move forward and see, like, attach some physical meaning to these entries, and actually then you will see that these numbers will become very familiar to us as we move forward. So what we are going to do is we are going to, so let's think this way. So what we are going to do is, we know that the first column of this matrix represents, so to find the first column, what we have to do is we have to displace the I node by amount vi, and you can fix all the other degrees of freedom, and whatever the force is required is the first column. And actually this is by a definition the stiffness, this is by definition the meaning of stiffness coefficients. So we are going to use this idea. So we are going to first take the vi degree of freedom and move it with the amount that is vi, and fix all the other degrees of freedom, and so on and so forth. So let's get started with this idea. So the thing is, in this case, what we are going to do is we are going to, because we are looking at the stiffness coefficient, we are going to displace the vi degree of freedom by 1 unit, and we want to find the other forces. So for example, what's going to happen in this case, the force in the first degree of freedom is actually by definition k11. So this is the force in the first degree of freedom due to unit displacement in the first degree of freedom. And the moment here is actually k21. So k21 is the moment at the second degree of freedom due to unit displacement at the first degree of freedom. And then similarly, we have k31 and k41. And I have put some numbers here. So let me go through the step-by-step process how we get these numbers. So as I told you, there are like three magic numbers. If we remember these three magic numbers, we will see that we are able to build this entire stiffness matrix. Okay. So the first magic number to remember is actually 12 vi by L cubed. So I put this number in like red color. So you can think that 12 vi by L cubed is the force required to displace a degree of freedom by 1 unit, while the other degrees of freedom are still 0. So you can think that theta I is 0, vj and theta j is 0. And if you take the vi degree of freedom and move it by 1 unit up, this is the force required. So it's 12 vi by L cubed. So this is a number we have to remember. And it turns out that if we can remember a single number, we can calculate all the other stiffness coefficients. And so you can see that k31 is by equilibrium. It should be negative 12 vi by L cubed, okay? Because they have to balance each other. So k31 just comes from equilibrium. So if we know k11, we already know k31. Now, in this bottom figure, what I have done is I'm representing the equilibrium of the movements here. So you can see that F is here, the vertical force up, it's 12 vi by L cubed, and F here is the vertical force downwards is 12 vi by L cubed. Actually, I'm trying to write k31, but I'm actually not putting the sign. I'm absorbing the sign in the arrow here. So what's happening here, actually, if you think K11 and K31 is actually creating a movement, okay? Because one of this force is acting upward, the other force is acting downward. So actually, it's creating an unbalanced force or an unbalanced movement in the system. And the unbalanced movement is actually F times L. So this is the movement is actually the force time movement arm. And movement arm in this case is just the length L of the beam. So unbalanced movement is actually F times L. So if we multiply this value by L, it's actually 12 EI by L square. So this is the unbalanced movement. And if you think carefully, this movement is actually in the clockwise direction, okay? And to balance this movement, we have to put some additional movement on the beam. And so what happens to balance this movement? We are going to put half of this value at the end I and at the half of this value at the end j. So we put 6 EI by L squared at end I and 6 EI by L squared at end j. So this 6 EI by L squared is actually your K21, and 6 EI by L squared on the end j is actually K41. And then finally, if these are all the stiffness coefficients in the first column, so this is all the stiffness coefficients in the first column. And so you can see that it's 12 EI by L squared, 6 EI by, 12 EI by L cube, 6 EI by L squared, and then minus 12 EI by L cube and 6 EI by L squared. So these are the 4 stiffness coefficients. And remember that to just get all these numbers, we have to remember just one number, and the other entries come from equilibrium, okay? So this is how we can find the stiffness coefficient in the first column. And it also gives us some physical intuition. What are the meaning of these numbers? So now we look into the second column. In the second column, what we have to do is to find the second column. We have to take the theta I, that is the second degree of freedom, and move it by 1 unit. So this is the theta I, and we are actually, it's a rotation. So we are rotating the beam by 1 unit. So you can think that we are rotating the section by 1 unit at the I end. And we have to remember 2 more magic numbers. So in this case, the movement required to do is, in this case, 4 EI by L, where L is the length of the beam and EI are the properties. So E is the modulus of elasticity and I is the cross-section inertia. So we have to remember this number. And then the movement on the other side is actually 2I by L. So it's half the movement on this side, okay? So the moment here is 2I by L, and movement at the I end is 40I by L. And if we again draw the free body diagram with these 2 moments, so this is the 2 movements acting 4EI by L, 2EI by L. So you can see that now there is an unbalanced movement on this beam. So total unbalanced movement is actually 4EI by L plus 2EI by L. So the unbalanced movement is actually 6EI by L. And this movement is acting in the anti-clockwise direction. To balance this movement, we have to apply some forces. So you can see that whatever the force system we should apply, that force system should create the movement in the clockwise direction, because this movement is in the anti-clockwise direction. So this is the force system I'm applying to create a movement in the clockwise direction. And if we want to calculate what is the magnitude of force, the idea is force times L. L is the movement arm here, should be equal to this unbalanced moment here. So this is 6 EI by L. And if we do this algebra and try to find the force should be 6 EI by L square. And so we know that the magnitude of this force should be 6 EI by L square. So on this I end, it moves, the force is applied upward, and the J end, the force should go downward. And actually, these are the stiffness coefficients. So K12 is this force here, 6 EI by L square, and K32 is this force here is minus 6 EI by L square. And actually, these are the 4 numbers that goes into the second column of the stiffness matrix. So these are the 4 numbers that goes into the stiffness matrix here. And so you can see that if we can remember, like for example, in this case, one number 2I by L cube, we can get all the numbers from just statics. And here again, if we can remember these 2 numbers, 4EI by L and 2EI by L, we can get these 2 other numbers from statics, okay? And this also gives us the physical intuition what number should be positive and what number should be negative. And we have two more cases left, but they are very similar to these first two cases. For example, for the Vj degree of freedom, now we already know if we want to displace the J degree of freedom by vertical displacement by 1 unit, the force required should be 12 EI by L cube. So this is actually K33 because this is the third degree of freedom, and K13 should be, to balance this K33, should be negative 2 EI by L cube. And finally, we have to apply some moment here. So you can see that this force system is actually creating a anti-clockwise movement, and the movement is actually 12 EI by L square. And to balance this unbalanced movement, we have to put some movement. So actually half of it goes on the I end, the other half goes on in the J end. So this is the movement on the I end, 6 EI by L square. This is the movement at J end, 6 EI by L square. So actually you can see that K23 is 6 EI by L square, and K43 is also minus 6 EI by L square. So both of them are minus 6 EI by L square. Okay, and this is exactly all the information in the third column. If you go back and look at the third column, these are the 4 entries. So this is the first entry is K1 due to 3, second entry is K2 due to 3, this is K33, and this is K4 due to 3. So we get all these 4 numbers. And similarly, we get for the last degree of freedom, that is theta j. So we move theta j by 1 unit and calculate all the other forces. And these numbers are actually the 3 magic numbers, if you remember. So these are the same magic numbers. So if you want to displace this by 1 unit, fourth degree of freedom by 1 unit, or in this case, the displacement is rotation. So we are rotating it. So you always remember that we are rotating in the positive sense. So the rotation is positive as we are using the right-hand rule. So it's actually anti-clockwise direction is the positive sense here. So the movement at the fourth degree of freedom is 4 EI by L, and the second degree of freedom is half of it. So it's 2 EI by L. So these are the 2 numbers that we already saw in the other case. And finally, we can find, based on these 2 unbalanced movement, you can see that the force here should be 6 EI by L square. And so this force again comes from the moment balance of this system. And we can see the direction here. So this side, the force is up. So K14 is 6 EI by L square, and K24 is minus 6 EI by L square. Okay. So these are the 4 entries that goes into the last column of the stiffness matrix. Now, at least with this information, we have some idea about what is the meaning of these stiffness coefficients and how they are generated. Okay. And actually, these numbers are very helpful. So we can actually use these numbers directly to actually simplify a lot of our analysis and to generate some intuitive understanding of what is happening. So let me summarize. So what we need to remember is what's happening to individual degrees of freedom. So when we take a degree of freedom and move it by 1 unit, what are the forces in that configuration? So when we move Vi by 1 unit, all the other degrees of freedom are 0. These are the 4 numbers here. Okay, so this is the first. These 4 numbers constitute the first column, and the second case is when theta I is 1, all the degrees of freedom are 0. So these are the 4 numbers. These constitute the second column, and these are the next 2 cases. Vj is equal to 1 and theta j is equal to 1. And these stiffness coefficients are very important. So these actually, now what we can do is we can take these numbers and directly use these numbers to build the stiffness matrices of our system. So moving forward, what I will do is actually I would ask you to actually print these 2 sheets, this one, 7 and 8, and keep it on your desk when you go over the next portion of the lecture, because you will see that we are going to directly use these numbers now. So we are going to directly use these numbers to solve our problems. So we will try to, in this way, simplify some of the process. And actually, it will also help us to develop some intuitive understanding. And you will see later that this information can also be used to solve like frame structure. So even it's not we are using here for beams, but we will see that we can also use this information for frames also, 2D frames. So let me, before solving some examples, let me give you one interesting idea here. So what I'm going to tell you is that, for example, what have happened here, I've drawn some shapes here. For example, when I take this degree of freedom and move it by 1 unit, I'm drawing this shape here actually. So blue is the deformed shape. So this is the centroidal axis of the beam. And here, similarly, this is the deformed shape or the centroidal axis of the beam after deformation if I rotate it by 1 unit. But I didn't tell you how I got these shapes. So actually, we can actually solve the differential equation of the beam to get the exact shapes. What does these shapes look like? So I'm just showing you the idea here, what these exact shapes looks like, because in these previous slides, these are some approximations, okay? So this is just for illustration purposes. So these shapes like in blue, these are for illustration purposes, but actually I'm still trying to draw it in some meaningful way. So let me show you if you want to figure out what are the exact shapes. Actually, we can do some algebra to find the exact shapes. So you can think like we have a beam member here. The length of the beam member is L, and I'm drawing some coordinates here, 0, and this is the x-axis, this is the y-axis, and we have the differential equation of the beam. So differential equation of the beam is like this 4th order differential equation, and actually we derived this differential equation in the previous lecture. So what we can do is we can solve this differential equation for 4 cases. So in the first case, what I'm doing is I'm taking this I degree of freedom Vi here to be 1, and the other degrees of freedom I'm fixing it to 0. So you can think that theta 0 is actually theta I. This is 0. VL is Vj, it's 0, and theta L is theta j, that is 0. So this is the first case. So I can use this boundary conditions and solve this differential equation to find what is V. And same thing I can repeat for other degrees of freedom. So in the case B, only theta I is 1, other degrees of freedom are 0. And in the case C, you can see that Vj is 1 and other degrees of freedom are 0. In the case D, theta j is 1, other degrees of freedom are 0. When I say 1 here, so in this case, you can think for rotation, this is 1 radian, okay? So the unit of rotation is always radian. And for the plotting purposes, I'm going to assume that EI is equal to 1, and I'm going to take L as 10, just to plot these, what these shapes look like. So what we have to do is we just have to solve this differential equation with these 4 cases, and we'll get the deformed shape, or V, for the beam. And V is the vertical displacement at some coordinate x, okay, along the axis of the beam. So if we try to solve the differential equation, it's a 4th order differential equation, so we can integrate it 4 times. So it will have, after integration, we will end up with 4 unknown coefficients. So this is what the system will look like. Vx is equal to, it's a cubic polynomial in x. And to find these coefficients, we have to use these 4 boundary conditions. So for the case A, if I use the 4 boundary conditions, I can reduce my solution to this form. So this is the cubic polynomial that we will get for Vx. And if I try to plot this shape, it looks like this. So I plot assuming L is 10. So this is actually the central axis. So this is the vertical displacement, or the displacement of the central axis. So actually, this is the, you can think like this is the exact shape, but I'm trying to approximate when I'm trying to draw my figures actually. So I'm using, for example, this kind of shape here. So this is the blue shape, blue line I'm using, but actually the exact shape is something like this, okay? Now what I can do is for the B case, where the rotation is 1. So in this case, theta I is 1. So if I again solve that these 4 coefficients with the 4 boundary conditions, this is the Vx we will get. So it's again a cubic polynomial, and if I try to draw the deformed shape of the central axis, so it's a red line we will get. And you can see that the rotation, if I draw a tangent at 0 and calculate this angle should be 1 radian. So 1 radian is around 57.3 degrees. So you can see that this angle is actually around 57.3 degrees. And this is the like the exact shape of the deformed beam, but I'm trying to, when I'm drawing, I'm just representing by this blue blue line here. Okay, so this is just an illustration of that deformed shape. So, but you're getting an idea what is the reasoning behind these kind of deformed shapes. And next, there are two more deformed shapes corresponding to Vj and theta j, but they are done in the same way. And so you can see that this is for Vj, applying a different set of boundary conditions. Again, it's a cubic polynomial, and you can see that in this case, Vj is 1, and this is the deformed shape. And this is the final case in which theta j is 1. Okay. And this is the deformed shape. So this deformed shape corresponds to the last case here, this case here. Okay. And again, if we draw a tangent at this end, you will see that this rotation angle is around 1 radian, and that is around 57.3 degrees. Before moving forward, I would like to make one comment here. So that V is actually a cubic polynomial. Sometimes we also call these kind of shapes as splines. And in mathematics, they're also known as Hermite polynomials, okay? And there's a lot more theory behind it, but we are not going to explore this in our class. If you go into if you go to graduate school, you might hear these kind of words. So you will see that these are actually Hermite polynomials, and also sometimes we call it cubic splines. So this is the idea behind those shapes. But now, from now onwards, I'm going to use those approximate representation of these shapes. I'm not going to put these exact shapes in my figure, but at least you got a feel of from where I'm getting those deformed shapes. Okay. So with this, let's try to solve the first problem in this session. So in this case, this is our example number 1. As usual, I'm starting with a very simple example. So you can see that there's a cantilever beam where the load is applied at end B. And we want to find the unknown displacements at B. Of course, A is a fixed end, so there is no known displacement at A. And we want to find the unknown displacements at B. So the idea is as follows. So first, we always discretize the system and assign the degrees of freedom. So here we discretize the system and assign the degrees of freedom. I'm assigning, again, the free degrees of freedom first. So I'm assigning U1 first, and then U2. And this is U3 and U4. So this is my assignment of the degrees of freedom. And then we want to solve the system. So in this strategy, the strategy we are going to use is actually, we will not try to build the stiffness matrices of elements, okay? So we will try to avoid that process of building the stiffness matrices of individual elements. Instead, we will try to actually get the coefficients in the global stiffness matrix directly, because we already know. So because to find the stiffness coefficients is corresponding to the first degree of freedom, we have to displace the first degree of freedom by 1 unit and calculate all the forces. And those are the stiffness coefficients. So we are going to directly use the definition of stiffness coefficient to build the stiffness matrix. And that's the reason those 4 cases that we talked about, those are useful. So I hope that you can print those cases and keep those cases by your side. So when we are working through these problems, you can refer to them and see how everything is working together. So let's move forward. So in this case, first, before solving it, let's try to actually set up the system. What is needed to be solved? So in this case, we want to solve for known displacements. So there are 2 degrees of freedom, or 2 free degrees of freedom, that are P1 and P2. So our system looks like this. P1, P2 is equal to KFF times UF. And in this case, POF is 0 and US is 0. So we don't have to add anything here. So what we have to solve is just this simple system. So in this case, if I go back, you can see that P1 is actually minus P, and P2 is 0 because there is no movement acting at this end. So this is our P1 and P2. We need to find KFF. So we need to find KFF is this 2x2 stiffness matrix. And if you think carefully, to find the first column, what we have to do is we have to take the first degree of freedom and move it by 1 unit and calculate the forces. And to find the second column, we have to take the second degree of freedom, move it by 1 unit, and calculate the corresponding forces. So we are just going to use this idea to build the stiffness coefficient. So we are going to directly build the stiffness coefficient without going into the element stiffness matrices. So let's start one by one. So for the first column, we take the first degree of freedom and move it by 1 unit. So we take the first degree of freedom and move it by 1 unit. And we want to find the corresponding stiffness coefficients. So we want to find K11 and K21. So K11 is this entry and K21 is the moment here. And that's where the coefficients that we have talked about will come handy. So you can directly see that K11 is actually 12 EI by L cube and K21 is 6 EI by L square. So these numbers are already in the sheets. I hope that you have printed those sheets. To quickly show you where these numbers come from, I can actually go back. So this is the configuration we are looking at, okay? So you can think that this is the beam deformed configuration we are looking at. So you can see that this number is 12 EI by L cube, and this moment is minus 6 EI by L square. So this is the force and this is the moment. And actually, these are the two numbers that I have put here. So this is 12 EI by L cube. This is minus 6 EI by L square. So I directly use the stiffness coefficients from the earlier sheets, okay? And now we have this first column here. So we have these first two entries. Now we want to get the second column. For the second column, we have to take the second degree of freedom and move it by 1 unit. And the second degree of freedom is the rotation. So K22. So we need to find what is K22. K22 is, as we said, to rotate it by 1 unit, we need the moment of 4 EI by L. So 4 EI by L is the moment here. And K21 comes from symmetry, because we already know that K21 is equal to K12. So this number has to be symmetric. So we can just use the symmetry to get this number. Or we can actually go back and figure out what this number is in the sheets, okay? So, but you will get the same number. So if we do this quick algebra, you can see that this is our system now, P1, P2, this is PF. So PF is minus P0 is KFF. This is our KFF here times UF. And we can solve this thing. And I'm solving this system in a symbolic form. And if I solve it, we'll get the U1 and U2. So these are the two unknown displacements. The first displacement is the vertical displacement. The second displacement is actually the rotation. So the U1 is actually VB and U2 is theta B. So and you can see that they're both negative. The reason is because the load was acting downward. So you can see that the end here, B, moves vertically down. That's the reason VB is negative. And actually, if you look at the section here, this is also the section is rotating in the clockwise direction. Okay. You always remember that anti-clockwise direction is actually the positive sense of rotation. So clockwise direction is actually negative rotation. So that's the reason theta B is negative. So for if P is downward, then both displacement and the section rotation is negative. And this is inbuilt into this solution itself. So this is just to show you an idea what is the sense of rotation and what is the sense of vertical deflection. But I hope that you are able to understand this in a more clear way with this figure. So let's move on to the second example. And in the second example, we have a beam again. So in this case, the one end is fixed. There is a hinge at the other end. So this end is actually at this end, at the end B, the section is allowed to rotate. But the vertical displacement is not allowed. So what we want to find is we want to find the unknown displacements at B. So we have only one unknown displacement at B, that is the rotation at B. And also we want to find the support reactions, the vertical force at B, and the moment at A. So these are the two support reactions we want to find. So again, the first step is we discretize the system. So we just actually take one element here. And in this case, there is an important thing we have to remember. So I put the properties in an interesting way. So I'm saying the modulus of elasticity is E. I is actually equal to 3I. And L is the length of the member here. And when I put the degrees of freedom, again, we put the free degrees of freedom first. So you can see that U1 is the only free degree of freedom, that is the rotation, that is the first degree of freedom. And then the second is this vertical degree of freedom, and then 3 is the vertical degree of freedom here, 4 is the rotation here. So they are the 4 degrees of freedom. And now before solving the system, we always set up the system and see what are the stiffness coefficients we need to find the solution. And then we can build those stiffness coefficients directly. So let's do that. So second step is set up the global system to be solved. So in this case, you can see that there's only one free degree of freedom. So P1 is equal to K11U1. This is the only system we have, okay? So we just need K11 entry in the global stiffness matrix. So this is the only KFF here. Remember that in this case, POF and US is 0. So US is actually U2, okay, so I made, there's a typo here. This should be U2, U3, U4. So I'll fix it later on. So US is all 0. So we already know that U2 is 0, U3 is 0, U4 is 0. And of course, there is no member forces. So PO1 or PO1, PO2, PO3, PO4, everything is 0. Because if you also want to find the support reactions like at 2, so RBY is actually, RYB is the vertical reaction here. This is just P2. So if you think carefully, the equation for P2 is actually K21U1, K22U2, K23U3, and K24U4. But what's happening, because U2, U3, U4 are all 0, so we don't need all these stiffness coefficients. So this equation is actually just, this will result in K21U1. And similarly, P4 is the moment here. So it's equal to MA. And it's actually equal to K41U1 plus K42U2 plus K43U3 plus K44U4. But again, because U2, U3, U4 are all 0, so this is just reduces to K41U1, okay? So this is an important step, actually. So what we are doing in this step is we are just setting up this whole problem. We are not solving anything. So in this step, we are trying to figure out what are the stiffness coefficients that are needed to solve the problem. So if you think very carefully, in this case, we just need K11, K21, and K41. And how can we get these stiffness coefficient? We can actually displace the first degree of freedom by 1 unit and find the forces at the first, second, and fourth degree of freedom. Those are the stiffness coefficients by definition. So this is what we are going to do. So now we are going to directly assemble the needed stiffness coefficient. We displace the first degree of freedom by 1 unit. So the first degree of freedom is actually, oh, there's another typo here. It should be U1 here. So U1 is equal to 1. I'll fix this. So we are displacing this by 1 unit. So in this case, U1 is the rotation degree of freedom. So we rotate it by 1 unit. And so K11 is the moment required. And the moment required is 4 EI by L. But in this case, remember that I is equal to 3I, because I said that, okay, I is actually 3I for this problem. So the total moment required will be 4 EI. So in this case, I am replacing by 3I. So the total required moment is 12 EI by L. And at the second degree of freedom, actually the fourth was, you can go to the sheets and see the fourth. It's actually minus 6 EI by L square. But I is equal to 3I. So I just put the correct value of I here. And we get minus 18 EI by L square. And the moment at the other side was K41. So this was this coefficient. This is the fourth degree of freedom. And this is 2 EI by L. But I was equal to 3I. And so we put the correct value of I. So we get this number 6 EI by L. Okay. So this is how we get these three coefficients, K11, K21, K41. We don't need K31, so I didn't put the value of K31. But if it was needed, we could have calculated. So if you go back, we just need K11, K21, K41. And once we have these numbers, we can calculate this, all the information we need. So first, we always solve for unknown displacements first. So we solve for unknown displacements. It's P1 is actually equal to M. So if I go back, so the corresponding force that is corresponding to the U1 degree of freedom is actually M. So M is the applied moment. So P1 is M. This is K11. So P1 is equal to K11 U1. So K11 comes from 12 UI by L times U1. And this is just a simple equation we can solve for U1. So U1 is actually the rotation at B. If we solve this, this is just ML divided by 12 EI. So this is how we can get the solution for this case. So after we solve the unknown displacements, we can go back and find the support reactions. So support reactions, we just have to do the simple algebra. So P2 is K21 U1 and P4 is K41 U1. So we are going to do this algebra in the next sheet. So this is the algebra for P2 and P4. So these are the stiffness coefficient we multiplied by U1. Okay. So we do the algebra. P2 is actually minus 3 by 2 M by L, and P4 is M by 2. And actually, you can see that dimension-wise is also consistent. So you can see that P2 is actually the vertical force. So it's actually movement divided by L. So when you divide the movement by L, you end up with the correct dimension-wise is correct. And P4 is M by 2. So P4 was actually the moment at A. So dimension-wise is also correct. Okay. And these are I just draw the support reactions here. So this is minus 3 by 2 M by L. This is M by 2. This is the moment M. And actually, I didn't calculate the vertical reaction at end A, but you can clearly see that this vertical reaction should be equal and opposite to this because they have to balance each other. So if we want to calculate it quickly, I just showed it here. So this is equal and opposite to this reaction here. So this solves our example number 2. And I hope that now you're getting the idea like how to use these stiffness coefficients. So idea is take the degree of freedom, move it by 1 unit, and assemble all the coefficients. Okay. So these are 2 simple problems. Now the next 3 problems are a little bit more involved, but I hope that you will be able to follow it. And let's see how to solve these problems again in the next slide. So in this case, we have like 2 beam members, so it's a continuous beam. So one span is AB, the next span is BC. The end A is fixed. At the B and C, they are like they're hinge supports here. So at B, this actually the node at B is allowed to rotate, and again C, there is a rotation is allowed. But in this case, what is happening? There is a support settlement. So I'm assuming that the support at B is displacing by -1. So it means that this is going down by 1 unit. And theta A is actually also, so in this case, theta is actually it's a motion of this support here. So I'm assuming that this support is actually rotating in the anti-clockwise direction by 0.5. Okay. I'm not putting any units in this problem just to keep the thing simple. And we want to solve this system. Again, for this case, the member AB has the property as E, 3I and L. So I for member AB is actually 3I. And for member BC, the properties are EIL. And I'm assuming E is equal to 1, L is equal to 1, and I is equal to 1, just for simplification. So you can think that in this case, for this member BC, I is equal to 1. For member AB, I is actually 3I. So it's like 3. And for this problem, what we want to find is we want to find the known displacements and the support reactions RYC and MA. So these are the 2 support reactions we want to find. Again, before solving anything, we want to set up the system to see what stiffness coefficients we need, and then we will walk through those stiffness coefficients. So let's do this exercise. So first step is always discretize the system and find what are the free degrees of freedom and what are the degrees of freedom that we need to worry about. So you can see that there are only 2 free degrees of freedom here. So one is the rotation at B and one is the rotation at C. Okay. So in this case, there are 2 free degrees of freedom. So this is how I'm discretizing the system and assigning the degrees of freedom. So the first free degree of freedom is actually rotation at the B. So I'm calling it U1. And then there's a rotation at C, U2. And there is a vertical displacement. This is U3, and U4 is the vertical displacement at C. And then U5 and U6. Okay. So this is the degrees of freedom. Interestingly, in this case, there is no loads applied. So there's no load on the system. Okay, only there are support displacements. So there's no loads. So you can see that if we try to solve the system, we have to take into account US, because US is not 0 in this case, because we know that U3 and U6 are not 0. Okay, so U3 is -1 and U6 is 0.5. So there are two numbers that are not 0. So if we try to set up the system, PF is equal to P1, P2, and P1, P2 are both 0. It's equal to KFF, UF. UF is U1 and U2 plus. So we have to take into account K13, K23 times U3. So because the third degree of freedom is non-zero, okay? So we need these two coefficients, K13, K23 times U3 plus the sixth degree of freedom is not 0 because this is the part of US. So we will need K16, K26 times U6. So this is the system we have to solve. Of course, POF is 0. So there is no member forces acting, okay? So this is a system we have to solve. So in this case, again, P1 and P2 are both 0. U1 is equal to -3. U6 is equal to 0.5. And we have to find what is KFF. So KFF is these 4 entries here. So if we want to solve the system, you can see that these are the 4 stiffness coefficients we have to find. And we also want to find the support reactions, P4 and P6. So P4 is the vertical reaction at C, and the P6 is the moment at A. So we write down the equations here. You will see that we will need K41 for the P4. We had K41 U1 plus K42 U2 plus K43 U3 plus K46 U6. There are other coefficients, but they get multiplied by 0 displacement. For example, there will be K45 U5, but we are not taking into account, or K44 U4, because U4, U5, those are all 0. Okay, so we are not. So I'm just including the non-zero terms here. So these are the non-zero displacements. So we have to find the corresponding stiffness coefficients. Similarly, for P6, we will need these stiffness coefficients. And once we set up the system, then we can think about how to generate those stiffness coefficients. For example, definitely to find the first column here, we take the first degree of freedom and move it by 1 unit. So if we take the first degree of freedom and move it by 1 unit, then we will be able to find K11, K21, K41, and K61. So all these 4 numbers come from just moving by the first degree of freedom by 1 unit. The second column here in KFF, we can take the second degree of freedom and move it by 1 unit. And we can find K12, K22, also K42 and K62. Okay, so all of them will come from the same configuration. And in this case, to find P4 and P6, we also have to actually displace the third degree of freedom by 1 unit and calculate the forces at 4 and 6. And we have to displace the 6th degree of freedom by 1 unit and calculate these coefficients like K46 and K66. So we have to actually have 4 displaced configurations. Okay, so let's do them one by one and find all these stiffness coefficients. So this is the case for U1 is equal to 1. So we take the first degree of freedom here and rotate it by 1 unit. And now we have to do something very interesting here. So first degree of freedom is actually the rotation at B. So when you rotate this degree of freedom, you have to rotate both sides of the beam, okay? Because the beam is connected. So you can see that we rotate both of these members. So AB is rotated, BC is also rotated. And we are interested in finding this moment here. K11 is the moment here, K21 is the moment here, K31 is the fourth here, K41 is the fourth here, and K51, K61. So these are all the forces that we want. And now we can look at those coefficient sheets and find all the entries we need. So if you see K11, the K11 is actually a contribution from 2 members. So one is the contribution from AB member. The contribution for AB member is 4EI by L for AB. So this is the moment that you will need to rotate this member AB by 1 unit. And similarly, to rotate member BC by 1 unit, you will again need 4EI by L. But you have to remember that I for AB is actually 3I. So and I for member BC is I. So if you think you have to multiply this by 4 by 3. So 4 by 3 plus 4. because EIL, they're all 1. So if you do 4 by 3 plus 4, this is 12 plus 4, 16. So this is K11 is actually 16 in this case. K21 is 4 EI by L for member BC. Oh, sorry, in this case, sorry, 2 EI by L for a member BC, okay? So you can look at those coefficient sheets and you will see that K21, if you look at this member BC, and if you look at this coefficient, this is 2 EI by L. And if we do the algebra, this is just 2. And we have to find K31. So K31 is the contribution of AB and BC. So we have to again look at those coefficient sheets, and you will see that for AB, it's actually minus 6 EI by L square. And for BC, it's actually 6 EI by L square. And we have to do the algebra carefully. Again, for AB, I is 3I. So this calculation is 6 times 3 because EI and L are all 1. But I is 3I. So this is 6 times 3. It's minus 18. And this calculation is just 6. So minus 18 plus 6 is minus 12. So this is K31. So K41 is the vertical force here. This is actually minus 6 EI by L square for BC. So this is just minus 6. And K51 is the vertical force here. It's 6 EI by L square for AB. So it's just 18. And K61 is 2 EI by L for AB. But I is actually 3I. So 3 times 2 gives you 6. And so this is how we are getting these stiffness coefficients, okay? So it will take some time and practice and to think about how we are generating the stiffness coefficients directly. But if you are able to think about it carefully, you will get it. You'll get better by practice, and we can actually get these numbers very quickly if you do some practice. So this is for U1 is equal to 1. So what we have done is we have generated all these numbers: K13, this one, K11, K21, K41, K51, and so on and so forth. But we have generated much more than needed. But this I just want to show you all the numbers here. And now we want to do for U2 is equal to 1. U2 is the degree of freedom at this rotation at C. So if we rotate it by 1 unit, you can see that the moment required to do this is K22. So K22 is 4 EI by L for BC. So this is just 4. K32 is 6 EI by L square for BC. So it's 6. K42 is the vertical force here. This is minus 6 EI by L square for BC. It's minus 6. And K52 and K62 are 0. So you can think quickly that this member AB is not even actually deforming when we are rotating this member. Only member BC is deforming. So there's no forces in AB member, okay? So K62 and K52 is 0. And again, we are getting K21 by symmetry. So K21 is equal to K12, it's 2. We have already calculated K12 in the last slide. So we already know K21 here. So K12 is equal to K21 is equal to 2. So we get this number by symmetry. This is the second degree of freedom. And then we have to just do U3 and U6 because those are the supported degrees of freedom. This is the U3. So in this case, we take the third degree of freedom and move it by 1 unit. And again, remember that in this case, because this node belongs to both beam AB and both AB and BC. So actually, both of the beam deforms. So if we move it by 1 unit, the force required, we are only interested in K43 and K63. So K43 is actually minus 12 EI by L cube for member BC. So, and because EI and L is all 1, so we get negative 12. And K63 is actually minus 6 EI by L square for member AB, okay? And because I is equal to 3I, and so this number becomes minus 18. So this is how we can calculate K41 and K63. There are other stiffness coefficients that are there, but I'm not calculating it because they're not needed in the solution that we are interested in. And lastly, we want to take the 6th degree of freedom and move it by 1 unit. And we are actually interested in K46 and K66 degree of freedom. There's a typo here. There should be K66. I'll fix it in the later. I'll fix in the slide before posting them. So you can see that first of all, the member BC is not even deforming. So whatever the fourth here should be 0 because there is no fourth in member BC. And K66 is actually 4EI by L for member AB. And because I is 3I, this 4 times 3 is 12. So this is just 12, okay? So K46 is 0 and K66 is 12. So this is a typo here. This should not be 63. This should be K66. And if we do this, all these calculations, we have all the stiffness coefficients. So now what we have done is we have figured out all these blue members. So we know all the stiffness coefficients. So we have to just do the algebra now. So the algebra is, to do the algebra, we first find the unknown displacements. So we write PF is KFF. So this PF is all 0. This is our KFF, UF plus the two coefficients times U3 plus the other two coefficients times U6. And we solve this thing. If we solve this thing, we'll get U1 and U2. And U1 and U2 is just the rotation at B and C, and this is the answer here. And then we can just go and back substitute this displacements in the equation for P4 and P6. Those are the support reactions. So we can get the support reactions by back substitution, and this is like 6.6 and 16.8. And this is how we do the calculation in this case. And I hope that it's giving you an intuition like how to do these problems in an efficient way. So you can see that we are not really building any stiffness matrix for individual elements. We are trying to build directly the stiffness matrix of that structure, okay? And it's just a fun way of solving these problems. I have 2 more problems to go, and the next problem is actually an interesting problem. And in this problem, I'm going to introduce a concept of hinge. I don't know if you have done these kind of problems in other classes, but even if you are not familiar with the concept of hinge, it's okay. I'm going to introduce you this concept in this class. So in this case, what's happening? We have a beam, and the span is L for both members here. So AB is one beam member, BC is another beam member, and they're connected at this point B with a hinge. And there's some uniformly distributed load on AB, and there is a concentrated load at the center of the span BC. And there are some moments acting, okay? They're concentrated moments. So there's a moment acting at C, and this is 8 kFit, and there's a moment acting on the right side of B, that is 4 kFit. And we want to solve the problem. So we want to find the unknown displacements and the member forces. So we are interested in also finding the member forces in this case. So first, to tell you what is the meaning of the hinge here. So the idea of hinge is as follows. So let me explain you with another slide. So you can see that if there are 2 members, they are joined by the hinge. So we have to define what is a hinge. So the meaning of the hinge is as follows. So whenever there is a hinge, these 2 members still deform, or actually not, I should say not deform. They displace vertically down with the same amount, okay? So there's still, you can think that vertical displacement is still connected. So still move vertically down with the same amount, let's say V. But because of the hinge, they are allowed to rotate separately. So you can think that there's a discontinuity in the rotation, and that hinge allows this discontinuity to happen. So you can see that if I'm drawing this deformed shape, you can see that the cross section at one side has actually rotated completely in a different way as compared to the cross section on the other side. And so if I'm drawing this cross section again, you can see that this is the rotation at the left side. So rotation if the left side is different from the rotation at the right side. And this discontinuity in the rotation is because of the presence of a hinge. And how it's actually happened is actually, so you can think like hinge is a physical mechanism. So someone has to actually build this kind of physical mechanism that can lead to this kind of discontinuity. And actually, typically, if you're a mechanical engineer, there you learn how to build these kind of physical mechanisms that that you can actually, that will allow this kind of motion. And we already know one kind of hinges, like you always see hinges at the end of the door, so that lets the door to rotate. So you can think like a hinge is a mechanism that actually lead to this kind of discontinuity in the rotation. So again, the idea is, what is happening at the hinge? There are two rotational degrees of freedom. So both sides, and the right side and the left side are allowed to rotate separately, okay, or they are allowed to rotate independently, but the vertical motion is still connected, so they still move together vertically downwards. So the idea is theta right and theta left are independent degrees of freedom, and the vertical displacement v is same at both sides, so both sides move together. That's the meaning of the hinge, okay? So when I say hinge, this is what it means. So let's move forward, how to handle the case of the hinge. So what is the meaning of hinge here? If I go back here, if I look at the free degrees of freedom in this case, you can see that there is one free degree of freedom at this end, that is a rotation at C. At B, there is one free degree of freedom, that is a vertical displacement at B. But because of the hinge, there are two rotational degrees of freedom. One is at the right side. So right side is allowed to rotate independently with respect to the left side. So at the hinge, there are two independent rotational degrees of freedom. One is at the right side, the other is at the left side. So, but that's the only difference between a hinge and a no hinge, okay? So hinge means there are 2 degrees of freedom at that location, 2 rotational degrees of freedom at that location. So let's try to solve this problem by incorporating the hinge. So you can see that hinge I'm drawing with this a red dot to indicate that this is a hinge. And I'm also now putting all the free degrees of freedom first. So U1 is the vertical degree of freedom. This is the free degree of freedom. U2 is the rotational degree of freedom on the left side of the hinge. U3 is the rotational degree of freedom on the right side of the hinge. And U4 is the rotation at the C here. And then these are the 4 free degrees of freedom. And then you have U5, U6, U7. Okay. So in total, there are 7 degrees of freedom, but only 4 degrees of freedom are free. So U1, U2, U3, U4 are free. So if we try to set up the global system, the system will look something like this. PF is equal to KFF, UF plus POF. So in this case, you have POF because actually there are some member forces. So we have to consider this POF effect. And let's try to find what is PF. So PF is P1, P2, P3, P4. So there is no load, no vertical load acting at the hinge. So P1 is actually 0. P2 is the movement acting on the left side of the hinge. So it's at the left side. So you can see that there is no movement acting on the left side. So P2 is actually 0. P3 is the movement acting on the right side of the hinge. So P3 is 4. So P3 is 4. P4 is the movement acting at the U4 degree of freedom. So this is 8. So this is 8. And I'm using the units here, kips and fit. So all the units are consistent. So you can see that this is our PF. And we have to find all these stiffness coefficients. And we have to find this POF, PO1, PO2, PO3, PO4 to actually solve our problem. And once we have this information, we can actually go ahead and solve the problem. And to build this stiffness coefficients, what we can do is we can just take these first 4 degrees of freedom and move it by 1 unit and calculate the corresponding forces. And that will give us all these stiffness coefficients here. So if we go forward and do it one by one, so we will have 4 cases here. So in the first case, U1 is equal to 1. So U1 is the vertical displacement here. So if we displace it by 1 unit and calculate all the stiffness coefficients, so K11 is in this direction, that's a vertical. This is K21, K31, and K41. So K11 is actually, we are actually trying to deform 2 beams, AB and BC, okay? So K11 is 12 VI by L cube for AB and 12 VI by L cube for BC. So, and if we add them together, this is 24 VI by L cube, and that is 240 if we do the algebra. K21 is the moment here. If you go to the coefficient sheets, this is minus 6 VI by L square for member AB. So this is just minus 720. K31 is actually 6 VI by L square for BC. And if we do the algebra, this is 720. K41 is 6EI by L square for BC. So it's again 720. So these are the 4 stiffness coefficients. So this gives you the first column of the KFF matrix. And this is U2 is equal to 1. Again, we are going to get K12 is equal to K21 by symmetry. So first, we can get the first entry from by symmetry. In this case, now there's a difference between a hinge and no hinge case. Because there's a hinge at B, so if we try to displace the U2 degree of freedom, we are not rotating the beam BC, okay? So only the member AB is going to deform because they can actually rotate independently because of the hinge. So you can see that because of the hinge, there's a discontinuity at the rotation at B. So this is how the deformed configuration look like for U2 is equal to 1. So K22 is actually 4EI by L for AB. So if we do the algebra, this is 5760. And K32 and K42 are the forces in member BC. So member BC is not even deforming actually. So these two numbers are all 0 because there is no deformation in member BC. And this is the case for U3. So U3, this is again in this case U3, only the member BC is deforming, AB is not deforming. So whatever the coefficients in AB, they're all 0. And but we can get K13 is equal to K31 by symmetry. Again, K23 is equal to K32 by symmetry. And we have to just get K33. K33 is 4EI by L for member BC. And we can do the algebra. So we get this number here, 5760. And K43 is actually 2EI by L for member BC. And this is just 2880. So we get these four numbers here, and this is the third column. And for the fourth column, we take the 4 degree of freedom and just move it by 1 unit. So 4 degree of freedom in this case is a rotation. So this is how this member will deform. And we just need K44 because all the other stiffness coefficients come from symmetry. So K44 is actually 4EI by L for BC. And this is just 5760. So you can see that this computations can be done very quickly because we are using the symmetry conditions, and we can just actually use those coefficient sheets to get these numbers. And after we have these numbers, we can go ahead and solve the system. But we also have to first get the member fixed and forces, like PO, to calculate that POF vector. So to calculate the fixed end forces, the member AB has some distributed load. So we know the fixed end forces for the distributed load, and we have the member BC has a concentrated load at the center. And we also know the fixed end forces for that case. And this is the calculation for fixed end forces. And again, we have to build that POF vector. So in this case, we have to just label where the degrees of freedom are. So you can see that if at the end B, so this is the B here. So this is the first degree of freedom is the vertical force. And again, the same thing is the vertical force is the first degree of freedom here. So at the end B, this side, if you look at the left side, this goes to the second degree of freedom. On the right side, this goes to the third degree of freedom. Okay, so these two movements goes to 2 different degrees of freedom, and the movement here goes to the 4th degree of freedom. So these are the assignment, and we just add them together to find the total force. So PO1 is actually just 12, and but we have to add 10 here because they both goes to the same degrees of freedom. So we add 12 plus 10. PO2 is only minus 24. PO3 is it's actually 30 kPa, and PO4 is minus 30. So this is how this vector is built. Now we have all the information, so we can go ahead and solve this problem. So let's try to solve this problem. So this is PF, and this is KFF times UF plus POF. And in this case, all the US are 0, so we don't have to worry about KFS US portion, okay? And we can just do the inversion of this 4x4 matrix, and if we try to solve the system, this is the answer. So the first degree of freedom is the vertical displacement at B. The second degree of freedom is rotation at the left side. And U3 is the rotation at the right side. So you can see that because of the hinge, there are 2 rotations, okay? And U4 is the rotation at C. So these are the numbers, and this is the answer for this problem. And what we have to do is, in this case, I'm also asking you to get the member forces. And to get the member forces, we will need this element stiffness matrix for these members. So that cannot be avoided if you want to find the member forces. So if you recall the member forces, if you want to get the member forces, we want to find what is Pyi, Mi, Pyj, Mj. So it's like stiffness matrix times the displacement vector plus the fixed end force. So for member AB, we have to find the stiffness matrix. So this is the stiffness matrix for member AB, and we have to put the correct degrees of freedom. So in this case, member AB is like here. This is A, this is B. So the degrees of freedom are VI. So it's VI is U6, theta I is U7, VJ is U1, and theta J is U2. So U6, U7, U1, U2. In this case, U6 and U7 are 0. Only U1 and U2 are non-zero. So actually, we don't need the first 2 columns of this matrix. We just need the last 2 columns. And if we do the algebra, we have to add also the fixed end forces. So we have to put the fixed end forces. So these fixed end forces are actually 12, 24, 12 minus 24. And it comes from, let's say, it comes from here. So we have already calculated this. So this is 12, 24, 12 minus 24. So these are the fixed end forces I added here. And if we do the algebra, these are the numbers, okay? And the units I was using was kip and fit. So all these numbers are kips and kip fit. And I just draw these numbers here just to show you the member forces in this member AB. And we have to do the similar exercise for member BC. And so this is the stiffness matrix. Stiffness matrix is the same in this case because the properties are not changing. And in this case, the degrees of freedom are, if we go back here for member BC, the degrees of freedom are U1, U3, U5, U4. So this is the order: U1, U3, U5, U4, Vi, theta I, Vj, theta J. So in this case, you can think that U5 is U5 is actually 0. U1, U3, U4 is the one that we calculated. So we have to put those numbers and add the fixed end forces. Again, this fixed end forces comes from the calculation we have done here. So the fixed end forces should be, in this case, 10, 30, 10, minus 30. So it's 10, 30, 10, minus 30. If we do the algebra, these are the numbers. So again, the units are kip and kip fit. So I'm now showing the like the member forces for 2 cases and showing the in the free body diagram format. So you can, interestingly, you can see that these are these 2 numbers correspond to the support reactions at A. And if you look at the hinge is at B. So you can see that at the right side of B, the unbalance, if you look at the moment here, it's actually 4. So you can see that 4 was actually the moment applied. So it's actually balancing it out, okay? And the left side of B, there was no moment applied. So the moment, actually, if you check the calculation, it was 0 here. So it's actually, the reason is there is no moment applied at the left side of B. So this moment is 0. And if you look at the, because there was no vertical force applied, you can see that if you add them together, the vertical force minus 11 and 11 is 0. So everything is actually nice and clear. So you can see that there's some kind of equilibrium between everything. And if you look at the individual equilibrium also, let's say if you look at this piece here for member BC, you can see that the vertical forces are 11 and 9. So they're balancing it out. 11 plus 9 is 20, and it's balancing it out, the 20 downward vertical force here. And you can see that the fourth here at C end is actually 8 kip fit, and actually 8 kip fit was the force that was the moment that was applied, okay? So this moment is actually the same moment here. So everything is under equilibrium and all the forces are balancing out, and this completes this problem here. And I hope that you're getting the idea how to think about the problem and how to actually handle this case of hinge. So remember that whenever there is a hinge, you have to consider 2 degrees of freedom, 2 rotational degrees of freedom, at either side of the hinge. Okay, so hinge actually let the section rotate independently. So that is the idea of the hinge. And next, I want to do the last problem here. So the last problem is a little bit more interesting problem. So this is the problem with the elastic supports. And we have done a similar problem in the last lecture also, but I want to solve this problem usually using this direct method. So in this case, what is happening? There is a two spans. One span is AB, the other span is BC. For the AB span, the I for the beam is actually 2I. For BC, the I is just I. So moment of inertia of the beam is changing actually. The span length is the same. And on span AB, there is some kind of a triangular load distribution. And in the span BC, there's a vertical load applied at the center. Okay, so this load is applied at the center. And these are the support conditions. You can see that. There's a spring at B. The spring stiffness is KS1, that is 24 EI by L cube. And the spring, there's a spring at C also, and the spring stiffness is 12 EI by L cube. And some properties are given. So EI is actually 12 cube times 10 fit square, and L is 12 fit. So these numbers are given, and we want to find the unknown displacements and the support reactions at D and E, that is, and the member forces. This is what we want to find for this problem. And before solving this problem, let's think about what are we have to start with laying out the whole process. So let's think about what are the unknown displacements in this case. So you can see that there are 3 degrees of freedom at B. So vertical displacement and rotation, okay? So both are 3 degrees of freedom. And at C, there's only 1 free degree of freedom, that is vertical displacement. This is not allowed to rotate at C. So there are 3 free degrees of freedom in this case, okay? So we are going to discretize this system into 2 elements. And then we're going to put the free degrees of freedom first. So the first degree of freedom is the vertical displacement up. The second is the rotation here. And the third is the vertical displacement at C. And then U4, U5, U6. So U4, U5, U6 are the supported degrees of freedom. And U4, U5, U6 all are 0. And U1, U2, U3 are the free degree of freedom. So we try to set up the global system that we need to be solved. So it's going to be, the global system is actually PF is equal to KF times UF plus POF. So we have to include POF because they're member forces in this case. So we will have fixed end member forces that will contribute to POF. So in this case, if you think carefully, if I go back, there is no forces that are applied at the degrees of freedom, U1, U2, or U3. So P1, P2, P3 are all 0. So P1, P2, P3 are all 0. There are no nodal forces or nodal moments applied, okay? So there are only fixed end forces that are needed in this case that will contribute to your POF here. So in this case, we will need this 3x3 stiffness matrix. And to build this stiffness matrix, we can do the same process. We can take the first degree of freedom, move it by 1 unit, and get the first column. And then take the second degree of freedom, move it by 1 unit, get the second column. And for the third column, we take the third degree of freedom and then move the unit by 1 unit and get the third column. Okay, so this is the process we are going to do. So let's try to apply this idea. So now what we are going to do is, for the U1 degree of freedom, we take the first degree of freedom and move it by 1 unit. See, what you have to think is, whenever you're displacing a particular degree of freedom, you're trying to look at what members are deforming. So in this case, you will see that both member AB and BC is going to deform because they're connected at B. And also the spring at this here, like DB is also, so the first spring, KS, is also going to deform. The spring at C is not going to deform, okay? But this spring at B is going to deform. So you have to remember carefully what members are deforming, and once you know this, we can directly build the stiffness coefficients. So K11 is the vertical force because that's in the first direction. So K11 is the contribution of member AB, member BC, and the spring. So member AB, the contribution is, you can go and look in the coefficient sheets. It's actually 12 VI by L cube. So it's 12 VI by L cube for member AB, 12 VI by L cube for member BC. And because the spring is also deforming by 1 unit, the contribution for the spring is just Ks1, okay? Because Ks1 is the stiffness coefficient of the spring. So we can directly build K11 by doing this algebra. But you have to be careful when you're doing this algebra, because in this case, I is different for different members. So you can see that A for member AB, I is actually 2I. So this calculation is 12 times 2, 24 EI by L cube. And this is still 12 EI by L cube, and Ks1 is 24 EI by L cube. So this is 24 EI by L cube plus 12 EI by L cube plus 24 EI by L cube for Ks1. And if you do the algebra, it's actually 60 EI by L cube. And this turns out to be 600. So this is the algebra for K11, and K21 is the moment here, and it's a contribution from AB and BC. So see, the spring does not have any contribution from movement. So you can think that the rotational stiffness of the spring is 0, okay? So the spring does not resist the rotational component of the motion. It only resists the vertical component of the motion. So there is no contribution from this spring here. So the K21, the contribution only comes from the member AB and BC. For member AB, it's minus 6 EI by L square. For member BC, it's actually 6 EI by L square. And but we have to do the algebra carefully because I is 2I. And so if you do the final algebra, it's minus 6 EI by L square, it's minus 720. And K31 is 12 EI by L cube for member BC, so it's minus 120. And so this is the U1 degree of freedom, and then we have to do U2 and U3 degree of freedom. This is the U2 degree of freedom, that is a rotation at B. And you can see that in this case, there is no hinge at B. So both members AB and BC rotate together, okay? So, and we have to find K22 and K32. So K22 is 4EI by L for AB plus 4EI by L for BC. And but we have to put the correct value of I. So this is 4 times, in this case, for AB, is like I is 2I. So 4 times 2 is 8 EI by L. So this is 8 EI by L. For this member, it remains 4 EI by L. So this is 8 EI by L plus 4 EI by L. It gives you 20 or 12 EI by L. And so this is 17280. K12 is equal to K21. So we are getting this from symmetry. So we are not really calculating it again. And K32 is actually minus 6 EI by L squared from member BC. So if we do the algebra, it just turns out to be minus 720. So this is the second degree of freedom. And then we have just one more degree of freedom left, and we can do it quickly. So the last degree of freedom is U3 is equal to 1. This is the vertical displacement at C. So in this case, you can think that this spring here, the second spring at this this spring is also deforming. Okay, so we have to have contribution of this spring also. So K13, K23 comes from symmetry. So we are not doing the calculation again for these two coefficients. We just, okay, there's a typo here again. This should be K33 here. So I'll fix it in my when I put the slides up. So this number should be K33. It should not be K32. So K33 is 12 EI by L cube for member BC plus Ks2, the stiffness coefficient for this member, okay? Because this member is also deforming by 1 unit. So this is the calculation. So this is 12 EI by L cube plus 12 EI by L cube. So it comes out to be 24 EI by L cube. So if we do the algebra, it's like 240. So this is again a typo, and I will fix it in my slides later. And now we have all the stiffness coefficients and all the information that we need, but we still have to get the member fixed end forces. So we have to do the calculations for the fixed end forces. There are two kind of distributions. For AB, there's a triangular load pattern, and these are the numbers. We have used it in earlier examples, so we just have to do the algebra carefully. So if we do the algebra carefully, these are the fixed end forces. It's like 36, 21, 9, and minus 24. And for member BC, there's a fixed forces due to this vertical force at the center and these are the fixed end forces. And so we are interested in the first, second, and third degree of freedom. So in the first degree of freedom, the 9 and 10 goes together. So we have to add 9 and 10. And in the second degree of freedom, minus 24 and 30 goes together. So we have to add these two numbers. So we have, if you add 9 and 10, you get 19, and minus 24 and 30 gives 6. And the third degree of freedom is only that actually I have put it the wrong place. The 10 should go. Okay, so this 3 should move downwards here. So I'll fix in my slides. So this is, but I'm writing the correct number here. So it's 10 here. So 10 goes to the third degree of freedom. So 10 is actually the free degree. So third degree of freedom is this one here. So it's this degree of freedom here. So 10 goes to the third degree of freedom, and this is your POF vector. So once we have this information, we can solve the problem. So we are solving the problem here. So this is PF is all 0 here. P1, P2, P3, they're all 0. KFF times UF plus POF. And if we do the algebra, this is the solution. So the U1 is actually vertical displacement at B. U2 is the rotation at B. And U3 is the vertical displacement at C. And the units I was using was fit and radian. So I get these are the units. Okay. So my units for this problem are kip, fit. So I end up with the results in fit. So after we have this, we can actually go and find the support reactions at D and E. That's where we need the support reactions for this case. So D is actually at the end of the spring, the first spring, and the E was at the end of the second spring. So if you think very carefully, if I try to draw the spring here, and if you think that VB is the displacement at this was the B node and this was a C node, and if you think that VB is the displacement here, so you can see that RYD, the reaction here is minus KS1 times BB. That's what this is, like a simple algebra here. Okay, so we can just multiply the stiffness coefficient with VB to get the support reaction here. And if you can think about it carefully, this is how it is. So if you can think that if VB is positive, and then the spring is under tension, and this reaction should be negative because the reaction should then be downwards. So that's the reason there is a negative sign here. Similarly, the same exercise I have done for the second spring is minus KS2 times VC. And so if we do the algebra, we get the answer. So the reaction at at D is actually 13.78 kips, and at reaction at E is actually 10.78 kips. Okay, so this is the way we can calculate the unknown reactions for these two cases. And with this, we can go and define the member forces, because this is also we want to find in this case. And the member forces calculation is the same that we have done for other cases. So for member AB in this case, I have to use the correct stiffness matrix because I is equal to 2I. So I build a stiffness matrix for this case, and the degrees of freedom should be, this is the member A and B. So A is this node, B is this node. So it should be 5, 6, 1, 2. So 5, 6, 1, 2 should be the ordering, because this should be VI theta I, VJ theta J, plus the fixed end forces. So these were the fixed end forces. So if I do the algebra, these are the numbers I'll get, and I'm just showing you like the free body diagram for this member here. And all these numbers are should be under equilibrium if we check it. Okay. And this is the member force for member BC. In this case, the stiffness matrix is different because I was different. And in this case, the degrees of freedom should be, this is B, this is C. So it should be U1, U2, U3, U4. So this is U1, U2, U3, U4. I just put these numbers, and I have to remember that U4 is 0, U1, U2, U3 are non-zero. So just do the algebra carefully. So if we do the algebra carefully and add the fixed end forces also, these fixed end forces we have already calculated back. So if we add them together, so we'll get the member force for this member. And this is the free body diagram of this member here. Again, if you check the equilibrium, you can see that 9.22 plus 10.78 equals to this vertical force here. And we can also check the equilibrium for the movement. So this force system should be under equilibrium for both movements and the vertical forces. And this last slide shows you the how the forces are flowing in the system. So you can see that for the at the end A, these two numbers are the reactions. Like these are the support reactions here, because these are two places there where the structure was supported. Here at the end C, minus 25.33 is the support reaction, because that was the supported degree of freedom in this case. If you look at the B here, so remember that there was no vertical force at B. So or no movement at B. So these two movements are canceling actually. Okay, but there is still some vertical force that is coming from the spring actually, but they're canceling each other. So you can see that 4.56 plus 9.22 is the total force upward because of the spring, and this force is actually getting transferred to the spring. So the structure applies this force in the downward fashion on the spring, and finally this is the same. This, if you add them together, this is 13.78, and 13.78 was the vertical reaction upward. So actually you can, in effect, you can think that this 13.78 is actually taken from this support reaction is transferred upward at this location B. Okay, and same thing, this shows you the flows of force in the spring. So this shows you the effect of the spring. What happens if you put a spring, and with this you can see the flow of forces, how the forces are varying and things like that. One important thing I want to mention is that what is the meaning of the spring here? So sometimes we can think like spring is actually used to model the stiffness of the foundation. So I'm pretty sure that you are taking some classes in geotechnical engineering, and if you think about geotechnical engineering, if you take some classes in foundation, you will see that there is some stiffness associated to the foundations also. So sometimes the springs are actually used to represent the stiffness of the foundation, and usually in geotechnical engineering, people have done a lot of experiments and they have experience about what are the stiffness of these foundations. So typically those numbers, like for example, these numbers here, like the spring coefficients Ks1 and Ks2, they come from handbook of like if you look at some handbooks, they will give you some numbers for different kind of foundations. Okay, for different kind of foundations, you might have a different kind of spring coefficient. So but typically that's where the springs are useful. We can model actually the stiffness of the foundations, and in effects in these actually these numbers affects the behavior of the structure. Behavior means how the forces get transferred, but at least now you know how to incorporate the springs if you have to. And you also have, I hope with this lecture, you have some physical understanding, like how the force systems are flowing and things like that. So this is the last example for our class, and I hope that everyone is able to follow. As always, you can always email me and contact me if you have any questions. And with this, I would like to end this lecture, and I hope that there is no confusion left. The most important thing I want to emphasize is, again, all these examples I'm just doing with the help of these numbers here. So if I go back, so all these examples, I'm just using these stiffness coefficients. Okay, so it's important, and it's better to understand how I am using them, and definitely bring these two sheets out, like this one and this one, sheet number 7 and 8, and with this keep these slides on your side, and when you're doing this, when you're going through this lecture, and this will help you to understand what's happening. Okay, so all these stiffness coefficients I'm using in various ways, and sometimes what is happening, I is changing, sometimes L might also change.